Assalamu alaikum to you all. This is the second and last part of our lectures on graph. So we're going to look at the remaining topics, which include topological sort, cycle detection, connectivity. This we touch a little bit on it in lab 10, but we're going to explore the topic in more detail, which again you're going to need to be able to do lab 11 inshallah. And the last topic is on spanning trees. Alright, so this is the agenda. Now let's take the first one, topological sort. What does this strange sound word mean? Okay, it says here there are many problems involving a set of tasks in which some of the tasks must be done before the others. A good example here relates more to you as students. Say, for example, consider the problem of taking a course only after taking its prerequisites. So in this graph, for example, assume these numbers are presenting courses. And for example, if you take this course 321, the arrow in the graph is indicating before you can do 321, you must have taken 143. So you have to do 143 before you can do 321. Similarly here, you must do 142 before you can do 143. And so on for all the courses in the graph. Now, if you are given a graph like this, it may be difficult for you to say, for example, what are the prerequisites to 341 directly. Wouldn't it be nice if we can have the courses listed linearly so that the prerequisite courses will appear first in the list before the courses that require those prerequisites? So rather than as a graph, let us have them as a linear list. This is basically the idea of topological sort. Okay, so the question here is there any systematic way of linearly arranging the courses in the order that they should be taken? Linearly means as one line instead of as a graph. And the answer is, of course, yes. And that is what topological sort is going to help us to do. Okay, so let's give a definition first. Topological sort is a method of arranging the vertices in a directed acyclic graph. So there's a condition for you to be able to apply topological sort. The graph has to be directed. Obviously, we have to know which course is prerequisite to another. So it cannot be a simple or undirected graph. It has to be a directed graph. Second condition is that the graph has to be acyclic. What does that mean? It means the graph should not have cycles. You can imagine if two courses, one is prerequisite to the other, and the other is also prerequisite to the other, then there's going to be confusion. Which one are you going to take first? So there must be no cycles in the graph. The graph has to be acyclic. These are the two conditions. This type of graph is normally called DAG, directed acyclic graph. Okay, so topological sort is a method of arranging the vertices in this type of graph as a sequence such that no vertex appear in the list or in the sequence before its predecessor. So the predecessor vertices will always appear first before the successor vertices. To show you the result of topologically sorting this graph so that the definition becomes clearer. This is what we have. So the graph in A can be topologically sorted as in B. So all the vertices in this graph, they are listed here. It's the same vertices, but they are listed now as a linear list. Okay, now what you can observe in this resulting graph is that all the arrows are going forward. No arrow is coming back. So that is an indication that the prerequisite or the predecessor vertices are always to the left, and their succeeding vertices will be to the right. Okay, you can see here no arrow is coming back. They are always going forward from the predecessor to the successor, predecessor to the successor, and so on. So this is the result of topological sort, and that is basically what we want to achieve. We want to have an algorithm that can take a graph that is directed and acyclic and give us another graph that looks like this, where the elements are listed linearly. Okay. Now, the first thing to note before we look at the algorithm is that topological sort is not unique. This obviously should be clear to you as students. As you know, there are many ways you can register for courses. Even though they have prerequisites, two students may not always follow the same sequence. Yeah, so the same thing, topological sort is not unique. As shown here, the following are topological sorting of the graph as shown in the picture here. So all these are valid topological sorting of this graph. If you can observe the first sorting, basically we are looking at the vertices vertically, if you like, from left to right, top to bottom. So A is done first, then B, C, as you can see, B, C, then D, E, F, D, E, F, G, H, and I. The second listed, on the other hand, is A, C, B. So it's the reverse. It's the same thing, but doing it from bottom up. So A, then C, B, then F, E, D, then H, G, and then finally I. Okay. S3 on the other hand is doing it A, B, D. So it's more like doing it diagonally like this. A, B, D, then C, E, G, F, H, I, and so on. And the last one here, A, C, F. A, C, F. So again, diagonally, but this time going down. In all of these cases, we are never violating the prerequisite, if you like. The predecessors are always visited first before their successors. Okay? All right, so that's the point. The topological sort is not unique. So you may have different results than what somebody else will find. Although we're going to make sure we're going to put some restriction in the way you do the traversal in our algorithm to ensure that you arrive at the same unique answer. Okay. Now let's look at the algorithm then. The algorithm for topological sort is rather simple. It's very easy actually. All we have to do is find a vertex V that has no incoming edges. So a vertex whose in degree is 0. Visit it first, in other words, add it to the sorted list, and then remove it and all edges emanating from it from the graph. Okay, disregard V and all edges starting from V means basically deleting that particular vertex after visiting it. And of course, if you delete a vertex, you have to delete all the edges that emanates from it. So keep doing that until your graph becomes empty. You will see that you have the elements sorted. Here is the summary of the algorithm. So topological sort will receive a diagram which is acyclic, and then in a loop from 1 to the number of vertices in the graph. We repeat. In each iteration, we find a vertex V whose degree is 0, and here we mean in degree. Since we are talking about directed graph, there's a clear difference between in degree and out degree. So here in degree, those edges coming to the vertex, how many are they? That will give you the in degree. So if you get 0, so meaning no more vertex is coming to this vertex, no more predecessor has not been taken care of. So visit that vertex. Okay, and then remove that vertex and all edges starting from that vertex from the graph. This is basically the algorithm. However, like I said, we want to make sure you get a unique result. And the way we're going to do that is here. You say when we say find a vertex V with degree 0, there may be many of such vertices that have degree 0. So ordinarily, according to the algorithm, you can choose any of them. But because we want you to get a unique result, maybe for easy marking, for example, we want to put a restriction. And this is the restriction. It says multiple vertices with degree 0 can be visited in any order. However, in order to get a unique sorting order, we shall be visiting them alphabetically if there are letters or words, or in increasing order if there are numbers. Okay, so this is the restriction. Don't just visit any vertex that has degree 0. No. If there is more than one such vertex, visit the one that appear alphabetically first. Or if there are numbers, visit the one that is in first in increasing order. Alright, so this is the algorithm, and I'm going to show you a nice animation example that will illustrate this idea. Okay, so let's take this graph. The graph has 10 vertices, as you can see, from A to J, and the edges are as shown here. We want to demonstrate how to do topological sort on this graph. So since the algorithm says you should find the vertices within degree 0, the first thing you should normally do is compute the in degrees of each vertex. Okay, so obviously you can see vertex A has only one vertex coming to it, and therefore its in degree is 1. Okay, we're not interested in the out degree. The out degree is 2, but that is not our concern in this algorithm, just the in degrees. Okay, because it is the in degree that will determine which vertex has to be done before this one. You can see we must do G before we do A, because G is a predecessor to A. Right, so in degree of A is 1. In degree of B is obviously 2, 1, 2. In degree of C is 3, 1, 2, 3. And in degree of D is 0. So this is our first vertex with in degree 0. See, this course, if you think of it as a course, can be done directly. It has no prerequisite. So we can do this first. But we have to check all the others, because if there is another one that is alphabetically smaller than D, obviously there won't be any, because A, B, C, D is the first. Yani A and B and C are not having in degree 0. But let's finish the computation for all the other vertices. E will have in degree 2, F has in degree 1, G is another vertex that has in degree 0. Okay, and then we have H, which has in degree 2, I with in degree 2, and J with in degree 0. Okay, so we have 3 vertices with in degree 0. So as we decided, we're going to visit the one that is alphabetically first. Yeah, so I'm marking here in red just to show you the vertices that have in degree 0. And obviously, as we said, D is the first alphabetically among these 3. So according to the algorithm, we should visit D. To demonstrate visiting, we just write D here in our resulting table. Okay, so visit D means put it here. Okay, and once we do that, the algorithm says delete D and all edges emanating from it from the graph. So we're going to delete this vertex and its emanating edges. Now when you do that, you will have to recompute the in degree of the vertices adjacent to D. Because, for example, if we remove this incoming edge, then the degree of C reduces to 2. The degree of H will reduce to 1. The degree of I will reduce to 1. And also the degree of E will reduce to 2. Okay, so let's go ahead and do that. D is deleted, and the degrees of the adjacent vertices are updated accordingly. So this is now 2, 1, 1, and also H is 1. Okay, so this is the first iteration in our algorithm, or in our loop. So again, we repeat, find the next vertex that has degree 0. So obviously we have G and J. So G is the first one alphabetically. Therefore, we're going to visit G first. Okay, so we visit G and put it in our table, and then delete G along with the edges emanating from G. So while we do that, we have to update the in degree of the adjacent vertices. So A will reduce to 0, in degree of B will reduce to 1, and in degree of C will also reduce to 1. Okay, let's do that. Delete vertex G and its emanating edges, and update the degrees of the adjacent vertices. You can see that we are now having A as another vertex with in degree 0. B has reduced to 1, and C has also reduced to 1. Okay. So now the question is, which of these 2 vertices are we going to visit? Now, even though J was the first one to have degree 0, no, we have to delay it and visit A first, because the algorithm simply says, or rather our restriction says, if you have more than 2 vertices that you can visit the one that is alphabetically first. So we're going to visit A first. Okay, so I have highlighted vertex A. It is the first alphabetically, so we're going to visit it. Visiting it means we're going to write A in our list of visited vertices, and then delete the edge and update the corresponding in degrees of the adjacent vertices. So F and B will both reduce to 0, as you can see here. Okay, good. So now again we have 3 vertices with degree 0, with in degree 0, B, F, and J. Obviously B is the first one alphabetically, so we're going to highlight it like this and delete it. Deleting it means the degree of h will also reduce to 0. So visit B, delete it, and update the in degree of h, which was adjacent to B. Next vertex is F. So we visit F and delete it. Now deleting F doesn't affect anybody because right now it has no edge emanating from it. So just delete it. Okay. Next alphabetically is H. Again, H has no edge at the moment. So deleting it will not affect any other vertex. So just visit it and then delete it. Finally, we are able to reach our vertex J because now it is the only one with degree 0 or in degree 0. Okay, so we visit J and then delete it. Now deleting J will now make E to have degree 0. Okay, so delete J and update the in degree of E. Okay, so again, E now is the only one with degree 0. So we visit it and then delete it. Deleting it will make I to have degree 0. Okay, so update the degree of I to 0. Then visit I because it is the only one now with degree 0 and delete it, updating the degree of C to become 0. So finally, visit C and then delete vertex C. The graph is empty and therefore our algorithm will terminate. So this is the way we can list the vertices of our graph in topological order. Obviously, this is one result. There could be many other results if we didn't have the restriction of visiting vertices alphabetically. Okay. So the next thing is to draw the resulting graph. How do we do that? It's really very easy. We just need to draw a vertex for each of the vertices in our table here. Okay, linearly. And then just look at each vertex here and see what are the arrows emanating, what are the edges emanating from it. Okay, so for A, for example, there is an edge going to B and another one going to F. Therefore, when you go to vertex A, you need to draw two arrows, one going to B, one going to F. Okay, B has only one arrow going to H. So from B, you can see we have an arrow going to H. C has no arrow at all. Okay, going away from it, yani. So it is the last vertex anyway because it has many in degree. That's why it has to be done last. It's like if you map it to courses, it is the course that has the most prerequisites, so it has to be taken last. This is why our topological sort actually put it at the end. Okay. D, however, has 4 emanating edges. So you have to draw an arrow from D. Where is D? Here is the first one actually, because it has no in degree. So D, you can see we have 4 arrows going to C. Okay, we have an arrow from D to C. So the last arrow here, we have another one going to H. So there's an arrow from D to H, and there's an arrow from D to I. Okay, the second top one there. And finally, there's an arrow from D to E. Okay, so this is all there is to it. Once you list the vertices, just redraw the edges, and you will have a topologically sorted graph. Okay, now the questions as they may come regarding this topological sort could be of 2 forms. In the first version, you could be asked just to list the vertices in the order they will be visited by topological sort. So if that is the question, then you just need to list the vertices like this. No need to do this. But if the question further says draw the resulting graph, then you have to do it like this as well. Just a point to note regarding how a question like this may be asked in an exam. Alright, so this is about topological. So there's one more example from the book. I will leave you to do it as an exercise, but this is the answer you should get. Okay, just try to solve it as we did. First compute the in degrees and then be visiting the vertices one by one alphabetically, those that have degree 0, and once you visit a vertex you delete it and also delete all the edges emanating from it. If you do that, you should get the answer as listed here. And this is the resulting graph from the list here. Okay, so that is basically about our first topic on topological sort. Next is cycle detection. How can we detect if a graph has cycle? We already defined what a cycle means from the first lecture. Basically a path that start and end in the same vertex without repeating a vertex and without repeating an edge. How can we detect if a graph has such cycles? This actually is a direct result of topological sort. Okay, so it says here, an easy way to detect the presence of cycles in a directed graph is to attempt a topological order traversal on that graph. You will see that the traversal will not complete because you will have a situation where you have not finished visiting all the vertices, but also you don't have any vertex with degree 0. If there is a cycle, you're going to have that situation, and the conclusion will be that the graph has cycles. Okay, so it says this algorithm visit all the topological sort as we just did. Okay, to detect for cycle, we say you should attempt topological sort. Why? Because topological sort will visit all the vertices in a directed graph if it has no cycles. But if it has cycles, the algorithm cannot complete. This is the idea. Okay, so let us see this by an example. It says in the following graph, after vertex A is visited and removed, all the remaining vertices will have degree 1. There is no vertex that has degree 0 after that. So topological sort cannot complete, and therefore the conclusion will be that the graph has cycle. Let's see what I'm talking about. Suppose you visit A. Right now, these are the in degrees. As you can see, A is having in degree 0, B is having 2, 1, 2, C is 1, D is 1. So, according to the topological sort algorithm, we should visit A first. So, suppose we visit A and delete it. If you delete it, the degree of B will reduce to 1. And now you will be in trouble because there is no vertex with degree 0 that you can visit next. And the reason for that is because there is a cycle. As you can see, there's a cycle here. Okay, so basically this is very easy cycle detection. All you have to do is update the topological sort algorithm so that instead of visiting vertices, it will be counting how many are visited. And instead of printing each vertex visited, just count, just like we did, if you remember, for the connectedness. We updated the breadth first traversal in lab 10 so that instead of printing the vertices, it will count. If we were able to count all of them, and if your count equals the number of vertices at the end of the traversal, it means your graph is connected. So the same thing here, if your count after topological sort is that the vertices you are able to visit is less than the total number of vertices in the graph, then you should return true. Your graph indeed has cycles. This is why topological sort could not complete. This is all there is to this subtopic, just to show you that you can use topological sort to detect whether a graph has cycles or not. Okay, therefore topological order traversal cannot complete in this graph, and the only conclusion is because of the presence of the cycle BCD, as I already explained. Okay, so let's move on to the next subtopic, connectedness. As I said, we have already touched on this in lab 10, but actually we considered it only for undirected graph. We're going to see that it has a slightly different meaning if we are talking about directed graph. And I hope you will pay attention to this subtopic, because actually that's what you need to be able to do lab number 11, which is the task number 3 in that lab 10 document. So connectedness, a simple graph or undirected graph G is said to be connected if there is a path between every pair of vertices. If you take any vertex, there will be a path that will take you to any other vertex. Okay, if you can do that, then the graph is said to be connected. Okay, so for example, this graph is obviously not connected. There is no path that can take you from any part here to any other part here. So from B, we can never reach E or D or F. And similarly from F, we can never reach C or B or A. Okay, so that's the idea. So although the figure below appears to be two graphs, it is in fact a single graph. It is just that it is disconnected. And clearly G is not connected. Okay, for example, there is no path between A and D. There is no such path. Okay, G in fact consists of two unconnected paths, each of which is a connected subgraph. Yeah, so this is a subgraph and it is connected. Similarly, this is a subgraph and it is connected. However, the graph as a total is not connected. This is basically the idea. So as we did in lab 10, to implement an algorithm that can check for you whether a graph is connected, it's really very easy. Just do a traversal, any traversal. In the lab we did breadth first traversal from one vertex only, though. You don't repeat the traversal from all the vertices. Just take one vertex, okay, like vertex 0 as we did in the lab, and see how many vertices can you be able to visit if you start a traversal from that vertex. Obviously, if you start from A, we will only be able to reach B and C and the A itself, so total 3. So 3 is obviously not the same as the total number of vertices in the graph, which is 6. And therefore the conclusion will be that the graph is not connected. Okay. So this is precisely what I'm pointing out here, that a simple way to test for connectedness in a simple graph is to use either depth first or breadth first traversal starting from any one vertex. If all the vertices are visited, then the graph is connected. Otherwise, it is not. Okay, so that completes our discussion on connectedness for simple graph. What about directed graph? In a directed graph, there are two types of connectedness actually. Okay, they are called strong connectedness and weak connectedness. Okay, so what is strong connectedness? A directed graph G is said to be strongly connected if there is a directed path between every pair of vertices. So very similar to connectedness in a simple graph. If you start from any vertex, this time following the arrow, so that's what is meant by directed path. Directed path is path in which you follow the arrow as it is drawn in the graph. So following the arrows, we can reach from any one vertex to any other vertex. Then the graph is said to be strongly connected. Okay, what about weak connectedness? A directed graph G is said to be weakly connected if it is only connected when the direction of the edges are ignored. Okay, so it is better to understand this with an example. So let's take an example. See, this is a directed graph. Okay, you notice there is no arrow from E back to B. So basically from this part, we can never reach this part, although we can reach from this part to the other part because the arrow is going from B to E. Okay, so now if you observe, therefore, there is no directed path from E to any of B, C, or A. Similarly, there is no directed path from D and F to any of A, B, and C. Alright? So therefore, this graph is definitely not strongly connected. For strong connectedness, there must be a directed path, a path that considers the direction of the arrow from each vertex to every other vertex. So obviously, this is not the case in this graph. So the graph is not strongly connected. Okay, so next question is it weakly connected? Obviously, yes. If you just close your eyes and think these arrows are just simple lines, there is no, these edges are just simple lines, there is no arrow. Then obviously from E you can't go back to B if you ignore the arrow. Okay, so if that is the case, that you can only reach the vertices if you ignore the direction of the arrows, then obviously the graph will be connected. You will be able to get path from every vertex to every other in this graph if you ignore the direction of the arrows. Okay, so in that case the graph is said to be weakly connected. But notice actually that in directed graph there are three possibilities. A graph can be strongly connected, a directed graph that is. It can be weakly connected, and it can be not connected at all. Because, for example, suppose we have another vertex, G, somewhere here, which is isolated. Then even if we ignore the direction of the arrows, we can never reach that vertex. So in that case, the graph is not connected at all. Okay, so a directed graph can be not connected, weakly connected, or strongly connected. Let's read the rest of the slide just to make sure we didn't miss anything. So it's saying G, which is this graph, is not strongly connected. Obviously, because no path between any of the vertices D, E, F back to any of the vertices A, B, C. This is why it is not strongly connected. However, G is weakly connected since the underlying simple graph is connected. Underlying simple graph means if you ignore the arrow and think about this graph as an undirected graph, then obviously it's going to be connected. So if that is the case, then it is said to be weakly connected.